Hello friends, welcome to my YouTube channel JK Academy India. In this video, we will discuss about the vector groups of three-phase transformer and how these vector groups are identified or verified by performing the test. So, vector group are method of categorizing the primary and secondary winding configuration of three-phase transformer and phase relation between primary and secondary winding. In vector group, primary winding connection should be shown in capital letters, followed by next winding connection or secondary winding connection in small letter, followed by a phase relation of secondary with respect to primary winding in clock notation. So in clock, if both the pointers are at 12, it will be 0 degree. If our pointer is at 1 and minute pointer is at 12, then it is considered as 1. Similarly, this will be 6 and this will be 11. The transformer vector is labeled by capital letter and small letter plus number from 1 to 12 in a typical clock-like diagram. The capital letter indicates primary or HV winding, while the small letter represents secondary or LV winding. In the clock diagram, the minute hand represents the primary line to neutral line voltage and its place is always in the 12. The hour hand represents the secondary line to neutral voltage and its position in the clock changes based on the phase shift. If clock notation of phase shift, if the digit is 0, then the phase shift will be 0 degree. It means LV phasor is in phase with the HV phasor. If digit is 1, it means 30 degree lagging, means LV lags HV by 30 degree because rotation is anti-clockwise. Digit 6 represents 180 degree lagging, LV lags HV by 180 degree. Digit 5 indicates 150 degree lagging, LV lags HV by 150. Digit 11 represents 330 degree lagging or 30 degree leading, means LV leads HV winding with 30 degree. As we have already seen this diagram in previous video, here we can revise. This first diagram shows the YY0 connection. Here both the windings are in star. This is DD0 connection, both windings are in delta. This is the DZ connection, HV winding is in delta and LV winding in zigzag. This shows Y by 6, both the windings HV and LV are in star. In this case, both the windings are in delta having 180 degree phase shift, and this is the DZ6 where the HV winding is in delta and zigzag winding is 180 degree leading or lagging with respect to delta, because the phase angle is 180 degree, so it doesn't matter. This is the circuit of YD1. Here HV winding in star and LV winding in delta, and one indicates that LV winding is lagging with HV winding by 30 degree. This is DY1, this is the delta connection, and this one is the star. This is YZ1. Here the HV winding is star connected, where LV winding is in zigzag having phase displacement of 30 degree. In this figure, this is the DY11, most popular. HV winding is in delta, LV winding in star having 30 degree phase shift. LV winding is leading HV winding by 30 degree. This is YD11. HV winding is in star and LV winding in delta. In this is YZ11. HV winding is in star, where the LV winding in zigzag. Now, three-phase transformer contain vector groups, as we have discussed. Ensuring vector group by doing a vector group test is necessary before taking the transformer into operation. Here we are going to discuss the vector group test procedure and conditions for different vector group in detail. The vector group test is one of the transformer tests. First, we discuss the vector group test procedure and then conditions to check the vector groups. Following are the steps to obtain the phasor diagram of a transformer. By doing voltage ratio measurement, the voltage measured between various terminals will be indicative to ensure the phase shift. The two voltage which are to be compared must be in phase and have the same orientation. This is achieved by ensuring that the high and low voltage terminals are correctly connected. Testing engineers should derive at least three conditions to compare, add, and or equate the particular set of voltage measured. These conditions should be in such a way to ensure the phase shift and phase sequence. Usually 1U and 2U means U terminal of HV winding and U terminal of LV winding are connected or shorted, but it is not necessary to be so. Testing engineer can choose his or her choice and the conditions shall be derived accordingly. If the derived conditions are satisfied, vector shall be conformed. So how this test is being conducted? This is a transformer shown here. This is the transformer. These are the LV bushings and these are the HV bushings. First terminal U of HV and U of LV both are short circuited, means connected to each other, and a three-phase supply via MCB or an isolator being given to the HV bushing of the transformer for safety reasons. Now, vector group test for the conditions. Following are the various vector group of three-phase transformer and the condition to be satisfied to confirm the vector group. This is the first vector group yn 0. Both HV and LV are in star connection. So first connect 1U and 2U. Keep the neutral floating. Apply three-phase voltage on HV side. Voltage may be applied in either of the winding, preferably HV side, as it is safe. Now the conditions. There are total 3 conditions. First, measure the voltage between 1U and 2N. Measure the voltage in 2N and 1N, and 1N, 1U and 1N. So this is 1U and 1N, 2N, first one. This is 2N and 1N, and this total is 1U, 1N. So what is the relation? According to vector, 1UN 2N plus 2N 1N equals to voltage of HV winding with respect to its own neutral. Now the condition number 2, measure 1W and 2W, voltage across 1W and 2W, and voltage across 1V and 2V. Now these both should be equal. How? This is your 1W 2W and this is your 1V 2V. Now condition number 3, the voltage measured from 1W to 2W and 1W to 2V as shown in diagram, 1W 2W should be less than 1W 2V. So if these 3 conditions are being satisfied, then we can confirm that the transformer is in YN0 group. Second, YN6. Connect 1U 2U, keep neutral floating and apply 3-phase winding to HV side. Now what we are doing actually, 1U and 2U are being sorted. So we can keep this triangle over this big triangle, so it will look like this. Here will be 2U and 1U, and here it will be 2N. As shown here. Condition number 1, measure 1U 2N. This is 1U and 2N, this one. Measure 2N 1N. So this complete is 2N 1N. This whole is 2N 1N. And 1U 1N, so this is 1U 1N. Now these two voltages, the sum of these two voltages should be equal to this one. This is the condition number 1. Condition number 2, the voltage across 1W and 2V should be equal to voltage across 1V 2W. Condition number 3, the voltage across 1W 2V should be greater than voltage across 1W should be yes, it should be less than 1W 2W. This should be greater and this should be less. Third condition, DD0. If we are putting this small triangle inside this, it will look like this. So this will become 1U 2U, this will become 2W, this will be your 2V. Now we can compare by measuring these voltages, and these should be equal, like these voltages, this one, and this should be equal to this. So the condition number 1, 1U 2W plus 2W 1W, this and this, should be equal to 1U 1W, this whole. Similarly, condition number 2, this voltage plus this voltage should be equal to this. And the third condition, this voltage 1VW 1W 2V should be greater than 1V 2W. Next, DD6. In this case, if you are putting this triangle over this one, it will look like this. So 1U 2U will be same, this will be your 2W, this will be 2V. Condition number 1, the voltage measured from this to this and this one, the addition of these two, this one and this voltage should be equal to the. Second condition, the voltage across 1V and 2V plus 1U and 2V, these two should be equal to this one. Condition number 3, the voltage across 1W and 2V should be less than 1W and 2W, or you can say 1W 2W should be greater than 1W 2V. Y and D1 vector. If I put this triangle like this, so it will look like this. 1W equals to 2W, and this will be your 2V, and this will be 2W. Condition number 1, the voltage measured from 1N and 2V and 2V to 1U should be equal to this. Condition number 2, the voltage across 1W 2W should be less than voltage across 1V 2W. Third condition, the voltage across 1W 2V should be equal to 1V 2V. Now, Y and D 11. If I put this triangle here, it will look like this: 1U 2U 2W, and this is 2V. So here, condition number 1, voltage across these two terminal and these two terminal should be equal to this, and voltage across these two terminals should be greater than these two, and voltage across these two terminals should be equal to this. Similarly, dyn1, here if I am putting this 2u, means aligning this line like this, so it will look like this, 2u, this will be 2v, and this will be, straight line will be 2w. So the voltage measured from this terminal 1w to 2n and 2n to 1u should be equal to voltage across 1u, 1w. Now the voltage measured from 1v to 2v should be less than 1v to 2w, and these two voltages should be equal, 1w to 2w and 1w to 2v. These are the three conditions. So thanks for watching. I hope you will learn something about the vector group conformation and how the testing is being performed to conform the vector diagram of the three-phase transformer. So thanks for watching. Let's meet in next video. Take care and goodbye.